There we go. Hey, welcome everybody once again to Astronomy Daily Live. It's 2 hours UTC, and once again we're here gathering together this growing group of friends to think and talk all things astronomy and space and science and who knows what other kinds of nerdy tangents we can run into. So yeah, hope everybody's doing well. Things are good here. It was a nice quiet day. So yeah. So let's see. I see Tom in the chat and Bobby. I might as well since I mentioned his name, Bobby on the panel once again. Hey, what's going on?
Hey, what's up? I just want to let you know that if you're yet to go to my channel, I just did 4 videos, and they're radio oriented.
Oh, very cool. Okay, cool. And you posted that link over in the chat?
Yes, I did. It's all yours, Von.
Nice. Yeah, so I will definitely have to check that out, and everybody else definitely check that out as well. So yeah, it was a pretty successful observing run yesterday. Hey there, Earth Radio. What's going on?
Hey. Pop in for a second. How you doing?
All right, good. Everything's good.
In between shows.
Oh wow. Okay. Yeah, boy. You stay busy. I don't know how you do it.
I gotta keep busy. Keep the energy going.
I guess so. You got to, take a couple breaths once in a while, though, right?
Oh yeah. Hey, Bobby, did you have some bad weather down there? Bobby.
Probably not that I know of.
Oh, okay.
I can check my AccuWeather.
Well,
wasn't sure if you had any there. We have pretty nice weather here.
Yeah. It's been, it's cloudy here again. So.
I got clear at my location. I don't think we're gonna have any bad weather. Well, we might have some thunderstorms Thursday, but after that, that's just gonna be it for next.
Oh yeah.
The week here now.
Yep.
Wow.
Cool. Yeah.
Yeah, I think we have some rain coming midweek. I don't think we have any more snow. I hope not. I had enough of that. So.
Yeah. It's about time to move on from that nasty 4-letter word.
I've been watching these black birds. I guess they're like ravens,
Mm-hmm.
They sit on top of the trees, like a couple miles away, but they look. They're close enough where I can tell that they're a bird, on top of the tree.
Right.
I can only imagine they're probably just sitting there listening to Earth Radio as I'm playing, wondering what I'm listening, what I'm playing,
I can only imagine. Yeah.
Just
That's
wondering
great.
why they're all sitting there looking at me like, what are they looking at?
Yeah.
They're up on top of a tall tree, an evergreen tree, it's pretty tall.
Right.
And they're like looking over the whole area, maybe looking for food or something. I don't know what. But it's amazing how they just sit up there and you see the whole. I can imagine what the view would look like,
Oh yeah. They've got the bird's eye view.
There you go. Exactly.
Oh, it's bad.
Actually,
that's but I don't think you never posted any yet on the Discord yet.
What now?
I actually did. I've done sort of I decided to observe three things yesterday. My primary target was this really, really cool, and actually the more and more I'm learning about HW Virginis, it's really an interesting object, and it's been studied pretty hard. But I'm going to continue looking at it too. It's a eclipsing binary star. So it's actually two stars, the component A and component B, and they're going around each other, and every 2.88 hours, right? So like seriously fast, insane.
So there's Jim from Carolina Sky Astronomy and Chuck Nagel in the chat.
Fantastic. Thanks, you guys, for coming in. It's always great to see you, and it's nice to see you almost every day. So that's absolutely fantastic. The only one that's really required to be here every day is this guy right here. But I think it's absolutely great, that we get together each and every day. Oh, they're slacking around as usual here. So
they said they're going to take a day off, and they're going to take it whether you like it or not.
They take it and take it and take it and
That's
take
right.
it. So yeah. So so yesterday or last night, I actually did collect some photons on that object, and I need to look at things a little bit harder, but I definitely want to show you what I saw, and we can sort of go from there. But yeah,
you shared something on Discord earlier. While
yes.
you're doing this, you shared a shot of a satellite. Was it?
Yeah.
I did remember, but yeah, you captured that satellite as well.
Do you remember what satellite that was, or do you have a number? Or?
Yeah, what?
I don't think he's got like some tracking software. That's the problem. But let's say if he gets G-predict on his Fedora machine, that it will be better. Now, out of my curiosity, on your laptop, Cosmic, what type of operating system is that?
What kind of operating system is what?
On your laptop?
Well, I'm not running a laptop. I just have a regular Fedora. I think it's Fedora 2028 on this machine, if I remember right. Yeah.
Yeah, but when you did your off session, you have your laptop. So I was wondering what type of operating system you got on there.
Oh, that was Windows 7.
Okay, I can't believe that still works.
I'm just a miracle worker. I make everything work.
Well, yeah, when you can write the code for it, you can make it work.
Yeah.
That's the advantage of being able to do that kind of thing. When you write the code for it, you can make anything work.
Well, I think Windows 7 is still a valid OS, so shouldn't be any kind of problem there.
And I forgot when next year, but Windows 7 is about to expire.
Oh, is it? Okay. Well, when it goes, it goes. That's how it goes. Yeah. Anyway, so yeah, did make some good observations there, and I will go ahead and show you. We'll sort of go through this. So all of this is extremely preliminary because yeah, just sort of a quick look to look at the data. Still have to make absolute certain that what I'm seeing is actually what I should be seeing. So that's going to take a little bit of time to run through. But let me show you what I've been up to today. So let me get that up here and running. And yeah, being able to identify that satellite here. I'll share my screen so you can all see the shenanigans here going on. So, so I'm gonna hide that and come over here. And yeah, it just so happened that during the observations last night, there was a little satellite that just slowly trucked through. So this is a 3-second exposure. So that's how much motion there was in 3 seconds of time. So and I've actually got a stack of these, and I'll probably make a movie out of it just for fun. But the satellite just slowly sort of tracked across here, just chink 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 across. This
it's going from left to right.
I don't remember which way it was going. I'll have to reconstruct it, to find out. But this star here is actually HW Virginis, and that's about magnitude 10.5 or so. So this satellite was must have been around like magnitude 11 or 12. Really,
Chuck got it right. Chuck said the Space Force.
Yeah, exactly. So yeah, very, very, very faint, moving really, really slow. So probably some kind of geosynchronous satellite of some sort. It's I would be able to find out because for instance, I'd be able to know the coordinates of this star and the coordinates of that star, and knowing that, I'd be able to get the coordinates of that object at a particular time. So if I wanted to, which I don't think I'm going to, I'd probably be able to find out exactly what satellite that is. But it's faint, which either means it's very, very small and or very, very far away. The fact that it was moving so slowly indicates that it's probably pretty far away. So yeah, it was just a little bit of a surprise, to get this, and I actually got another one too. So I think I saw 2 satellites. This one was the slow mover, and then there was a fast mover where I think I only got like 3 images of it. Just really, really long streaks. Same exposure time, which means the speed was just faster. So yeah, it's just a little bit of a surprise. Those things, they happen all the time. So anyway, so in terms of the light curve I got, what I did is I measured the brightness of this star relative to the brightness of that star versus time. And if you plot that, what you get is that. So here's time. This is the Julian date, which is just one of the many ways to measure time. Yeah. And so and then these numbers here are the relative magnitudes. So it's is kind of hard to read, but the larger the number here, the brighter the target. So like you can see here, right at the beginning of the observation, I was actually just caught it right at the beginning of the event here, and it dimmed and dimmed and dimmed until a certain time, and then it brightened up again. And then I just decided, to observe it a little while longer. And then I took a little bit of a break here. I think I went over to Pallas, the asteroid Pallas, and made some observations there. And then I went back and I collected a little bit more data, because what these eclipsing binaries do is it there? No, it's not there. I thought I moved these. Oh, I guess I didn't. Let's see, where did I put that then? Let's see if I can find it here really quick. Going through all of this. Variable stars.
Now, with these photon collection photographs, what can you get out of that study? Like, can you get the size of the star? Can you get the type of star? Can you get the basically the properties of the star you're looking at?
Yes, I with that light curve, this one or others, I can get what I can do is I can create a model, and that model has lots and lots of different parameters, like the masses of the two stars, their orbits, temperatures, brightnesses, all of that. What happens in these binary stars is you have sort of a primary dip in brightness, which is caused by the B component passing in front of the A component. So the A component is the brighter of the two, and the B is the fainter of the two, and that's what causes this deep dip here, right? This one. But then, as the B component passes behind the A component, you actually get another dip, like this as well. And when I first looked at this, I looked at that and I was like, wait a minute, that's getting brighter. It shouldn't get brighter. So this puzzled me for a little while, and I still don't really. I'm not entirely sure, but my guess is that my timing was a little bit off, and so actually what I'm seeing here is this part right here, right? So it's just coming out of this secondary dip, going up and then coming back down, and I think that's what I'm seeing here. Now, one of the cool things about this particular system is that the light from the bright component shines onto the fainter component, and that light is actually reflecting off of the B component, and so what you get is sort of this characteristic curve here, right? See how it goes up and up and up, and then you have the secondary eclipse, and then down and down and down. This if there wasn't any kind of reflection from the bright star to the fainter star, this line would be relatively flat, right? It would just go straight across. But because there's a little bit of a reflection, as the B component goes around, the A component, we're actually seeing more and more of the reflected portion there, and so it brightens up. And then the B component passes in behind the A component, does this little dip, and then dims back down, and then
So
goes back into its primary.
wants to know, what software are you using to capture the data?
To grab the raw data, I think you're talking about like these images here. I'm using CCD Soft, which is just one of many camera control pieces of software. This just came with the camera and works really, really well. So that's what's used. Yeah. So it's called CCD Soft. To actually generate these plots, that one, I've actually written my own software to do that. So yeah, it's that way I've got a lot of control over parameters and what goes on and all that kind of stuff. And if there are things that I want to change, it's extremely easy to change them. So I think that's what I'm seeing here. So right after the primary dip, you can sort of see that this is beginning to rise. And what I should have done, and most definitely what I'm going to do next time, is I'm just going to hang on this target. I'm not going to go away, and come back. It's a short enough orbit. From here to about here is about 1.4 hours. So it's not very long. This whole thing, can take a couple hours. So that's easy. I would really, really, really like to see what happened here. What I think happened here is that it rose and rose and rose, and then it dipped, and then let's see, this part here, right, is this part. See how it goes up and then back down, just like that? So I think that's what I'm seeing there.
You got a bridge gap in one of your data.
You're breaking up there, Bobby. I couldn't hear any of that.
Oh, and I see that you got a bridge gap in one of your data plots.
A what gap?
Like a bridge gap or something in your data plots.
Are you talking about this?
Yeah.
Yeah, that's because I decided to move to a different target and sort of wait for the secondary thing to happen. Now the interesting thing is that the timings of these things are a little bit off. This event takes about 20 minutes or so. So I mean, it's really, really, really fast. This takes about as long. So, but my timings are a little bit off. So I have to investigate that a little bit too, because I wanted to catch this whole thing here, and I would have liked to catch a little bit earlier as well. But I sort of I took the information from the variable star group and used that, but yeah, it sort of looks like the timings are off a little bit. So I'm gonna have to think about that too a little bit. But what I think happened here
Okay.
is that it
So
rose and rose and
Jim's
rose.
got a question. If you got if you can check the chat.
Oh yeah, let me look at the chat. Forget my skull. Well, okay, so Jim, you're not actually going to see the individual components. They are what's called a contact binary. So these are two stars that are actually touching one another. They share a um, common atmosphere. So they're extremely close to one another. So I mean, never say never, but I mean, we'll probably never actually see the individual um, um, components. They're extremely close to one another, fractions of an astronomical unit. So
will they merge? Will they merge together?
You know, I don't know. I don't know. That's, I think, possible. The A component is about half a solar mass in size. The B component is, I think, about a tenth of a solar mass in size. So they're not really big,
Okay.
relatively speaking. So yeah, they.
Interesting. Yeah.
Don't know about that. But yeah, so when I first saw this, I was like, how can that be brightening up? But yeah, I think what I'm seeing is just sort of the last half of of this dimming event here. See, so this part here is that part, and then it's doing that, and then it's starting to come down again. So I think that's about right. So next time, I am definitely just going to sit on this target, and because I would really like to know what's going on here. So yeah, lesson learned. I need to sit on these targets. I don't need to move around as much as I am.
Good night, Ron.
Okay, good night, everyone. We'll chat with you next time.
All right, Ron.
Bye-bye.
Thanks for coming in. See you later. Yep, bye. So yeah, pretty exciting, pretty interesting stuff. Looks good. The data is noisy-ish, but I think I'm getting a precision of about 0.05 magnitudes, which isn't bad, and that's sort of what I've already known. Is that my wiggling around here is about 50 millimagnitudes, which yeah, that's okay. That's okay. Can I make this scatter better? I don't know. I'm going to have to think about that. I'm kind of I'm curious as to why this looks so nice and clean, and these don't. So I've got to look at the data, see what's going on there. Um, you know, and see if there's a way to modify my data collection technique to reduce the noise a little bit, because that's a lot of scatter there. So each data point is a 3-second exposure followed by about a 5-second download. So I was doing a sample about every 8-ish or so seconds or so, and the tracking. Oh man, the tracking last night was absolutely terrible. So was really, really hard. Like you can see, like you can see here, my target star was sort of on one side of the field, and my reference was on the other. So I didn't have a lot of wiggle room here. So, you know, trying to keep both of those in, you know, the field of view was challenging. You know, I think I lost a little bit more data than what I would want. But that's how it goes too. You know, you sort of have to deal with the cards, you know, that you're dealt. So, but yeah, you know, it's an absolute thrill to you know, to see this kind of a thing, because that's exactly what I want to be able to see. But lesson learned here for sure is that I'm going to sit on this thing, because I want to see this curve, which will hopefully you know, look like that. Yeah. So pretty cool. I still have to look at the timings of all this stuff. Like I said, it sort of looks like I'm the timing I got for MIDI clips here was supposed to be at 4:14 UTC, and this time right here was about 4:08. So it was about 6 minutes earlier than predicted. Now, there might be some things that I'm not taking into account, so I sort of have to look into that a little bit more. But, you know, preliminary look, I think it looks absolutely great. You know, the depth of this.
Jim's got another question, Cosmic.
Another question. No, absolutely not a chance at all, Jim. Not a chance at all. We can actually, well, you know, I don't think I'm going to look now, but like I said, you know, the separation between these two stars are in fractions of an astronomical unit, right? So fractions of the distance between the Earth and the Sun. And this object is hundreds and hundreds of light years away. So, you know, the separation between those two stars is most likely micro arc seconds. Extremely close. So yeah, like I said, never say never, but I don't think that anyone will ever see these two components. But you can look at their combined light curve and see that there's at least two. This object was actually discovered back in 1986, and it's been studied pretty extensively, and it's actually been found to also have at least two large planets going around this binary star. So, you know, like Tatooine, the binary star in Star Wars, something like that. You know, you have these planets that are actually going around this binary star. Now, sitting on those planets, you would probably most definitely be able to see, you know, the two components, but you got to get there. But yeah, looking at the light curve, there is definitely two components at least, and like I said, studies, careful studies of these light curves have indicated, comparing them to models, that I think there are at least two planets part of this system also. Now, am I going to be able to ever see that kind of indication here? I think my data is too noisy for that, but I don't know yet. This is sort of a preliminary look, and I don't know where this is all going to go. So yeah, but I'm pretty pleased with that. Definitely see some action there, and it's always nice to see that. And the time scales here are just are extremely exciting, right? From here, well, from here to here is like 20 minutes. It's really, really, really fast. So really, really neat. And the fact that I'm actually seeing the brightness here go up, I think that's a real effect. And that's because the B component is reflecting the light from the A component. Let's you know what? Let's let me see if I can. Let's look at one of these papers. I've collected a few of these. Let's see if we can, because one of these papers had a really nice little model showing the two components. Let me. I don't remember which one it is, so you're going to have to. Bear with me while I try to find these. I don't think it's on this one. I don't think so. Let's look. Let's look at this one. Don't remember which one it is. Same kind of light curve there. Oh, that one's not it. Let's keep going here. It's this one. I saw. Here we go. Here we go. So here's the A component, and here's the B component, and we are the observer looking, very, very, very far away. So as you can see, the B component is sort of going around with the A component this way, and we're observing it from this. So this is sort of a top-down view. I guess that's not really showing much. But yeah, as the B component passes in front of the A component, all of A's light, or most of A's light, gets blocked, and so you just see the light from B. Yeah, and same things happens over here, except in the opposite sense. When B moves behind A, you don't see B anymore. You just see A, and that's why you get this primary dip here. Primary dip is when B passes in front of A, because B is fainter than A, and then the secondary dip is that one when A passes in front of B. So yeah, very, very cool. Very, very cool. So yeah, this and I'm going to sort of move on to the next thing, because I was sort of curious to see if TESS was observing this object yet.
How long has it been since we have a TESS update?
Well, I don't know, but we're going to have one right now.
Yeah,
so
I think it's been a while since we've been seeing some TESS data.
Well, we are definitely going to look at some right now, in fact. So
let's do it.
So yeah, let's do it. So TESS's primary mission, of course, is to look for, planets going around other stars. And the way they do that is they spend about a month or so looking at different sections of the sky. Now, TESS has four cameras on it, 1, 2, 3, and 4. And then each of those cameras has 4 CCDs. And each camera is looking at a very, very large portion of the sky. It's actually 24 degrees per side. Okay, so each CCD is seeing a 12 by 12 degree area. So very, very large area. So the resolution isn't all that great. Each camera, or each CCD, is about 2,000 pixels on the side. So we could actually work that out, right? 12 degrees divided by, it's about 2,000 pixels or so. So that's 0.006 degrees. There are 3,600 arc seconds per degree. So if I multiply that by 3,600, so every pixel is about 21.6 arc seconds on a side. So resolution, not all that great. My camera, just as a comparison, every single pixel here, and we can actually zoom in on those. So every single pixel here is about 2 arc seconds. The TESS pixels, which I'm going to show you here soon, is about 10 times that size. So, but that's what you get for looking at very, very large pieces of the sky. But what they do is they look at the same piece of the sky, or strip of the sky in this case, over and over and over and over and over again for about 1 month at a time. And actually, here's what they've done so far. So they've divided the sky up into sectors, as you can see here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and of course they started with sector 1, and then 2, and then 3, and then 4. And here is sort of the schedule for the first half of the sky, right? They're looking at the southern half of the sky first, and then they're going to look at the northern half of the sky. And so here's where we are now. And as you can see right now, they are gathering data for sector 10. And they're observing sector 10 from March 26th until April 22nd. So they've got a few more days on sector 10. And and then each of the cameras, right? They're all stacked like that, are looking in different parts of the sky. So I'm actually going to move on. So this is sector 10. We can zoom in a little bit on that, I think. Oh, maybe not. It's a graphic. I guess not. Anyway, so here's sector 10, and this orange or reddish square is camera 1, right? That's this one. Here's camera 2, here's camera 3, and here's camera 4. Now, of course, it's distorted because of projection. So you know, right on the sky, these are still squares, but you know, because of the projection showing them like this, you know, the squares are distorted. But this is what it's observing at the moment, and you can sort of see these are the center coordinates for each camera in degrees. So to convert right ascension to hours and minutes and seconds, you would take this number and divide by 15, because there are 15 degrees per hour of right ascension. So the cool thing is, the interesting thing is that sector 10, camera 1, is actually going to include HW Virginis. It's actually going to be part of this next data set that's being collected right now. So that is pretty cool. So we should actually have this data. Like I said, you know, they end their observations on April 22nd. So I don't know how long it takes to actually process all of this and make it available, but I would think in the next, well, you know, I would think 1 or 2 weeks after you know, the 22nd, that data is going to be available, and I am definitely going to take a look at it. I'm sure lots and lots of people are as well. So the cool thing is that the data for all of this is actually available right now. They've actually released sectors 1 through 7. So that's all of let's see, all of these. Right, so going from 1, 2, 3, 4, 5, 6, 7, those have been released so far. And I don't know what happens if we if we click on sector 7. Where do we go here? Okay, that just does that. Okay. So yeah, very, very cool. I thought that I had this all worked out, but I think what we're going to do next is we're actually just going to go and grab some of that data. Let's see, what's the best way to do this? Let's do it like this. So this is just the data products document. And as you can see, you know, there's a particular naming convention here. So like if you wanted to grab a calibrated full frame image, you would look for some file names like that. And shoot, I think I'm trying to remember how we get to that point again. Bulk downloads, that's what it is. So let's take a look here. So we can go to the bulk downloads page, and we get to this. What this is just a bunch of curl commands, which is a lot like
wget.
Just like wget. In fact, it probably does almost exactly the same thing. They've decided to use curl. Doesn't matter what you use, but what you end up with is this huge file. I'll show you here, like this. It's just a shell file that you could either run the entire thing, which I don't recommend, because each one of these lines is going to grab a FITS file that's about 40 megabytes in size. And let's see, there are.
Then why you won't? Then why not doing a shell script or just doing an individual? Why? But then I mean, let me rephrase that. Then why doing an individual file is better than just doing the whole kit caboodle?
Well, I mean, it sort of depends on what you're after. There are 17,489 commands here. Yeah, I mean, they're yeah, I don't know why anyone would really want that. But let's go through these names. All right, so here's a file name. Actually, let's look at the first one here. Okay, so there's that. I can actually zoom in a little bit too, so we can really. Whoop. Actually, I can't. Let me do it this way. Zoom in.
So 40 megabytes. That should not hurt the system.
No, absolutely not. You can download as much as you want. But let's just go through the naming convention here a little bit. So here's the file name that you're gonna get, and let's look at this guy. So it's called TESS, and then there's a 4-digit year, a 3-digit day, and then hours, minutes, seconds. All right, so that's just a timestamp. That's all that is. Oh, here it is. So this was 2019, day number 8, at 2 hours, 59 minutes, 36 seconds. I don't know why I did that. Let's get out of that. There we go. Okay, so that's how timestamp is read. Let's dive into this a little bit more. So then we have this thing called SSCTR, which if you go to the docs, they are talking about it being the where am I looking here? SSCTR, the sector, right? So in this case, of course, it's sector 7, right? Just like that. And then we've got a little bit of a code there that tells you which camera number and which CCD number per camera. So in this case, we're looking at camera 3, CCD number 4, and think that's about it. The 131. Let's look. Yeah, it's some kind of a an ID here. 4-digit, 0 padded. Yeah, some kind of configuration map. Doesn't look incredibly important, but what we can do is we can actually do a search for let's see, how did I do that before? I was obviously playing with this before. Is this what I was doing? I think so. No, that's not what I was doing. What was I doing before?
Who decided to jump in?
Who decided to jump in? Who is jumping? Ah ha ha. Hi there, Blackie. Oh. Let's see. Yeah, I'm not remembering how I did this now. No, that's not it. That's not it. There was a I thought that I had figured out a way to because there should be 16, right? There should be 16 images per timestamp. Let's go back to this. There are, well, let's go here. So there's 4 cameras, and each of them has 4 CCDs. So there should be 16 separate images per timestamp. And for some reason, I'm not remembering how I was doing that. Let's do it like, let's do it like this. Let's just look for the timestamp. We can actually, let's look at the first one. So I'm just going to do a search for that, and there should be 16 of them. Find out. I believe there is. Let's do, yeah. So 16 of them here. Crash and burn. So if you go through this, I'm going to zoom out a little bit here, just so we can sort of fit this whole thing on here. So if you sort of look at all the combinations, see here's 1 1, here's 1 2, here's 1 3, here's 1 4, and then what it's going to go 2 1, 2 2, 2 3, yeah. So they're all there, all taken at exactly the same time, right? And the timestamp is exactly the same on all of these. So yeah, very, very cool. And I've actually downloaded a couple of these and popped them up on my display. So what I've done here is I've actually grabbed the same camera 3, and CCD 4, but at 2 different timestamps. You see, I hope you can see that. This one is it day 8, 2 hours, 59 minutes, 36 seconds. This one over here is day 8, 3 hours, 29 minutes, 36 seconds. So it's about what? like half an hour apart in time, if I'm reading that right. Yeah, in fact, it's almost, in fact, it's, looks like it's exactly 1/2 of an hour between this image and that image. So let's zoom in here. So this is one CCD camera. So this is 12 degrees on a side. So a huge, huge, huge piece of the sky.
You're always raking late, Deep Sky Dude.
What's that?
Deep Sky Dude just popped in.
Oh, yeah. Hey, Deep Sky Dude, you did make it. So we're looking at TESS data here from, I think that's called section 7. Section, is that the right term? I don't have my terminology down yet. Oh, wrong one. Let's go over here. Sector 7. Sector 7. And yeah, we're just examining these a little bit. So this is a full field. Now I can actually zoom in here. And let me go to just a single image here. So let's go ahead and zoom in, and we can start seeing the individual stars. So here, every single pixel is about 22 arc seconds on a side. So very, very low resolution. But the point of TESS, at least one of the points, is to actually watch the light curves of every single one of these stars and see if they change. Now, during the course of 30 minutes, we're probably not going to see much change. All right, so let me show you around here a little bit. If you sort of look at these boxes up here, what you'll see, the top one here is the actual data value, and like you can see, as I move over a star here, I'll sort of change the scaling a little bit, so we can just sort of zoom in on the bright ones a little bit. So as we move over a bright star, you'll see the data values change, and they're high there and they're low there. You can also see that it's showing the right ascension and declination of these stars. And as you can see, this particular one is pretty far south. Pretty far south. And then you have the pixel positions themselves as well. So that's sort of how to read that. And I've loaded both of these images in as you saw, so I can do that. Let's rescale that, kind of like that. All right, something like that maybe, and then we can actually match up the color tables here a little bit, so they match up. I think am I zoomed in? Let's see. So let's go zoom one here.
These images are from camera 3 and camera 4, right?
No. So this is camera 3 CCD4. So that would be camera 3. I'm not quite sure which one is which here, but CCD4 is one of these. I'm not sure which one it is. So Sector 7. Sector 7 is this section. Camera 3 is in this blue box here. can sort of see it better here. And then yeah, there are 4 CCDs that are looking with camera 3, and in these images we are looking at CCD number 4 in both cases. So they're looking at the same piece of the sky, just 30 minutes apart. So yeah, let's see. Let's zoom in on both of these, and as you can see, they look pretty much exactly the same. We can actually use this tool to blink between them. So now we are actually blinking between them. You might be able to tell there's a slight difference between them. Very, very, very slight. We can sort of zoom in really, really close. You can sort of see, that the background is sort of changing a little bit. So the calibrations aren't exactly the same between them. But for the most part, I don't see any difference there whatsoever. So this is just a very, very small portion of that image. We'd have to back up a little bit to see the whole thing. Oh, there we go. So now I'm blinking in between each one. This is some kind of a reflection of some sort, some kind of bright star. Not exactly sure. It's an internal reflection of some sort, not part of the sky for sure. One of the interesting things I see is that there's a concentration of stars here, and one here, and one here, and one here, maybe a little bit here. But so let's actually zoom in on these. So I'm going to go to a single image again, and let's sort of zoom in here and see. Yeah, see, there's a little, like a cluster here. Ooh, there's a cluster of something here too. Ooh, look at that. There's some fuzz back there. Kind of hard to tell exactly what's going on there, but yeah, kind of neat. Kind of neat. So yeah, it's really, really cool to have this kind of data just readily available. It's fully calibrated, so you don't necessarily have to do anything to it at all. And you can grab the raw data as well and calibrate it yourself if you want. But it's kind of neat, just to sort of see the calibrated data here. Let's zoom out again. So very, very cool. Very, very nice. And yeah, what TESS is doing, like I said, is they are identifying each individual star, and then they will generate a light curve, right? They'll show, or they'll measure the brightnesses of these stars over time, over that month. Looks like they're looking at these stars every 30 minutes for a month, and so you get a nice light curve, and that's sort of the next thing I'm going to do, is actually look at the light curves of these things. I didn't have enough time to set that up here today, but when Sector 10 is released, that will include light curves of that binary star what is it? HW Virginis.
Yeah.
and we'll be able to look at those and see what's up with those. So very, very cool. It's, you know, it always amazes me how many stars there are. It's just, you know, I mean, this is a, let's see, camera 3 is centered on a right ascension of 106.35 degrees, 106.35 divided by 15. So that's about 7 hours, 5 minutes right ascension, and then a declination of negative 44 degrees. I'm not quite sure if that's, I think that's looking in sort of a rich part of the Milky Way. It's just, it's way south of Orion, way south of Sirius. So I think that looks like it's probably in the galactic plane. So yeah, we're just seeing just zillions and zillions and zillions of stars here. Just absolutely amazing. But I wouldn't be too surprised if you know these weren't, you know, already known clusters of stars. We can actually change the brightness and contrast here to allow those to pop out a little bit. We can change the scale again so we can really see what's going on there. And as you can see, you know, the resolution here is more or less 1 pixel with a little bit of a spread. So, you know, the stars basically fall on single pixels, and there's a little bit of a spread, you know, because of the optics and all that. But yeah, absolutely fantastic. Let's see. Let's go back here. We can center it up again and zoom back out. Let's look at these other clusters here. We've got to go back to that to really see them. Yes. So that one we looked at. Here's another one here. So very, very cool. There, you know, there is so much.
Wants to see the images from TESS that they pointed towards the galactic center near the constellation of Sagittarius.
Yeah, you know, we have to see if they're actually looking there yet. You know, the first phase, you know, the first 13 sectors of TESS are looking pretty far south. So, but let's see, we can find out what the RA index of the galactic center is. Center. Let's do this. Galactic center. Let's see if we can get some coordinates here. Let's see. Gallery. We don't have coordinates here. Come on. Galactic center. Let's go back to here and we'll go coordinates. Whoop. That doesn't work. And we'll go right ascension. Oh man, they're just not telling us what we want to see here. I think this is the same thing. We have a right ascension. Here we go. So 1745 and negative 29. So let me convert right ascension to degrees. So 1745 times 15. So that's 266, and then negative 29. So let's look and see. Let's look and see if these guys go there. 266 and negative 29. It's got to be pretty close too. It looks like, just glancing at this, that galactic center isn't going to be observed until sector 12. So that is going to be observed coming up in a couple months. And then it looks like actually it takes a couple months to process the data and make it available. Sector 7 has come out, but they're currently observing sector 10. So yeah, it looks like it takes a couple months, to process the data. So sector 12 looks like it'll be seeing the galactic center, and so that'll probably be coming out in about August or so, I'd say. So yeah, we're gonna have to wait a little bit on that, but yeah, that's a lot of stars. One of the data products that they generate are light curves for I don't know if I can say all the stars here, but many of the stars here will have light curves associated with them, and you can actually grab those too and plot them. So very, very cool, very, very awesome. This is definitely data overload, but I don't mind. I like it, and that's
what would you prefer, cuteness overload or data overload?
What's the choice?
Cuteness overload or data overload?
Oh, I don't want to have that kind of choice. I want both. Definitely both. For sure. For sure. So yeah, this TESS is definitely a lot of data. It's absolutely incredible. So yeah, if you're so inclined, you can be the armchair scientist and look at light curves from all these stars, and spend spend your days looking for neat light curves. I can pretty much guarantee that every single one of these stars, it does have a light curve of some sort. They don't remain constant. But the time scales are different. So 30 minutes, things aren't going to change all that much. 30 days, oh yeah, they'll probably change. So very, very cool. Very cool. And yeah, I'm looking forward to Sector 10 because that has HW Virginis in it. And I think a lot of people are going to jump on that. But I am definitely, they're going to have a month's worth of data. And, these light curves, they change every 3 hours, right? The period of that binary star is 2.8 hours. So what is that? Let's I think I'm about ready to get on out of here, but let me show you that I'm definitely still grabbing. So let's just say 30 days, right? 30 days times 24 hours a day. 24 hours a day. I'm going to hold this up. So that's 720 hours. If the period is 2.8 hours per rotation, I can take 720 and divide by 2.8, and we will see about 257 eclipses. So that's going to be a really, really nice looking light curve, lots of dips and all that. So yeah, looking forward to that. I'm definitely going to, over the next day or so, grab some light curves of just some random stars and see what they look like. You never know. You never know. So, all right, everybody. Well, I think I'm going to get out of here for now. Let me check the chat really quick. Make sure that there aren't too many shenanigans over there that I'm missing out. Yeah. Well, there's lots of stars. There are lots of stars. So, all right, everybody, I'm going to get out of here as well. So thanks for coming in. I'll be back here again tomorrow, 2 hours UTC. Make sure to subscribe if you haven't already. Smash the thumbs up if you like. Make some comments. Spread the word. I am trying to just spread the passion. I love astronomy. I love space. I love science. All the nerdy things. Absolutely love it. Just trying to spread it out. That's what I've got. So that is what I like to share. So, all right, everybody. Take care. Peace, cheers, and all that. And I will see you in about 22 and a half hours. All right. See you later. Bye.